Swayam Prabha. Digital India. Educated India.
All right. So just to recall again, so this is again the kind of an atom. We have a nucleus. These are core electrons, valence electrons, and so forth. And then you have here, you can actually instead of using X-ray, if you want to do OJ electron emission, one can also use a electron gun. Electrons will go and knock out the core electrons here, right? And this electron will come out, and then this electron will fall down here into this, and then that energy is picked up by this electron. This will come out here. This is the Auger electron, right? So in Auger spectroscopy, of course, when you are recording X-ray photoemission spectra, you will also have Auger peaks there. But if you want to do only Auger spectroscopy, people don't use X-ray, they use electron gun of a particular energy in the Auger spectroscopy. Okay, all right. So that's the reason why step 1, 2, 3, 4 are order of steps in which the electrons will move in the atom when hit by the electron gun. Electron gun means it gives electrons of a particular kinetic energy, something like 3 kilo electron volts, around 3 to 3.5 kilo electron volts. Electrons will come and then they knock out these core electrons. Okay, but that is the to get the good Auger emission, people use this in the Auger spectroscopy. Okay. Now this is very important. This Auger process is also a very important process. For example, you have an element where you remove an electron from the core level. So this is the ionization process. Once this is photoionization, for example, photoionization process. Once you remove this electron, this is the excited state, and this will have to decay from excited to ground state. It has to come to some lower energy state. So there are two decay processes. One is X-ray process. That means the energy difference between the two. For example, here, the energy difference. This energy difference will come out as X-ray. Okay. So this is X-ray decay, the radiative decay, or it can actually, this energy can be picked up by this electron and it will come out as a Auger electron, right. So that is Auger decay. So you will have Auger electrons coming out here, whereas in this case you may not have Auger electron, you may have only X-ray coming out. These are two decay processes. These are the two decay processes by which the excited, the photoionized atom will get decayed. Okay. Now, if you see here, that depends on the atomic number. For example, you see this is the atomic number, Z is increasing from all the way up to 35, it is written there, and then the yield of the K electron vacancy, right. K electron vacancy means K is nothing but X-ray notation. In our atomic notation, it is 1s electron. 1s electron in X-ray notation they call it as K shell, whereas we call it as 1s electron. When you are talking about Auger spectroscopy, people don't talk about 1s, 2s, they talk about K, L, M, N. These are the K shell, L shell, M, N shells, K, L, M, right. So in Auger spectroscopy they use this language K, L1, L3, right. So what happens here is that when you increase the atomic number, for example, you go to atomic number Z is equal to 30, more than 30, you see X-ray yield is increasing, right. If you go to lower atomic number, less than, let us say 20, you see Auger yield is more. which means oxygen, carbon, nitrogen, etc. elements will give Moser yield compared to higher Z elements compared to X-ray. So they give more of Moser electron yield than X-ray yield. So what people normally do is to use X-ray spectroscopy to find out the contamination of the samples by oxygen, carbon contamination. No, they record X-ray, the OJ, because the yield is very high. So even small amount of carbon, oxygen, or any other contamination of the lower atomic number elements are present, then they can clearly see that. They can clearly see that. Okay, this is an experimental curve basically. This is an experimental curve basically drawn by doing experiments on various elements. Okay, all right. So these are the two decay processes that you should remember. Now coming to, for example, this is the sample electronic structure. I have a metal, for example. I have a metal which has core electrons, which has a valence band. It's a band, right? So this is actually called density of states. Probably you are not familiar with the density of states. It's a physics terminology, but what it means is the number of occupied states. These are all occupied. This is you see these are all electron states, but it looks like a band. It's not a localized levels like here. All the valence levels, they come together, form a band, and then they are delocalized here. The electrons are delocalized. They don't belong to a particular atom. They are delocalized. Whereas here the core levels are localized. The electron belongs to that particular energy level of that particular atom. All right. So this is the kind of electronic structure. Now you try to do photoemission spectroscopy of this, you should get peaks like this. So this should give you a peak, this should give you a peak, that should give you a peak, this band should give you a band. Exactly, it should map the electronic structure of the metal, of the compound. There is no other experiment to prove that these energy levels bands are present in the samples. Only for photoemission. Only photoemission. Okay. So now this is the EF, as I said, that is the highest occupied energy level. From EF there is something called E vacuum level. Vacuum level is nothing but, suppose you remove an electron from a surface. When you remove an electron, there is a positive charge left behind, right? That positive charge will not allow this electron to go away. You need to spend some energy to remove the electron beyond the influence of that positive charge. That is nothing but your work function, approximately, right? Now you take that out to infinite distance, then it is free. So that level, wherever that level is vacuum level, there is nothing, you don't, vacuum level means basically electron is free, it is in the vacuum. So now you take that one to the analyzer and then detector. Analyzer and detector, right? So that energy is nothing but your work function. So this is EF, this is work function, that is vacuum level. So that is what I said, density of states. This is all called density of states. Density of state means these are density of occupied states, because all these electronic states are occupied by electrons. Density of occupied states, DOS, density of occupied states. You may also have some states here also, but then you don't have electrons to fill them up. These are density of unoccupied states. They are called density of unoccupied states. So if that means you are removing electron from here in XPS, suppose the unoccupied state, you put electron in that. So you can do what is called inverse photoemission. Inverse photoemission spectroscopy. That is another spectroscopy. I am not going to talk more about that. There is something called inverse photoemission spectroscopy. XPS to the power of -1, where you put electrons in the unoccupied states. When the electron takes the electron and put it in the unoccupied state, it releases energy, photons. You measure the photon energy. From measuring the photon energy, you can actually map the unoccupied energy of the unoccupied state. Okay, so that is possible. That those experiments are all, those spectrometers are also available. One is there in IIT Bangalore. Okay, so we will not go much further on that. Then we have EF. So then this EF is taken as 0, because we have all those work functions, etc. For every sample, measuring work functions can be measured, right? So normally what people do is this one is taken as 0. That is the Fermi level. From Fermi level, you start measuring the binding energy. See the binding energy 0, 200, 400, 600. Scale is going down. So you see this 5D orbitals, 5p orbitals, 4f, 4d, 4p, and 3d, 3p, etc. They go down. So if you have, you don't need to go to n is equal to 1, n is equal to 2 states, because you get enough information. If you analyze this n is equal to 4 and 5 levels, if you analyze, that is, what is n? Principal quantum number. N is a principal quantum number. So n is equal to 1, n is equal to 2, you are basically going to 1s, 2s, 2s, 2p, etc. You don't have to go to that. For of course lighter elements like oxygen, nitrogen, etc. You can go to 1s very easily. But if you go to, for example, gold, copper, etc., you don't need to go to 1s. If you analyze the d orbitals, p orbital, that is sufficient. Okay. So your spectrum should look like this. So now the intensities are different here, you see. These intensities are different because of the something called ionization cross section. Suppose I have 2 electrons and I have in one orbital, I have p orbital, I have 6 electrons, and d orbital, I have 10 electrons, right? So I should get intensity more. No, there is something called photoionization cross section. If the ionization cross section is high, your intensity is going to be high, otherwise it is low. Cross section is nothing but the probability of absorbing the photon. Okay, all right. Okay, so that is this is how it looks like. This is how you map the whole thing here. So the importance of this slide is that I am showing you EF is taken as 0. That is from where you start measuring the binding energy of the levels that you are looking at. Okay. All right, look at this one, binding energies. Now 1s binding energy. For example, these are all lighter elements, lithium, beryllium, where that is equal to less than 20. Right. Now if you are looking at all these, and then if you see 1s binding energy, remove a 1s electron from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, you start seeing, initially lithium comes somewhere here, fluorine comes there. Does it make sense? Why is it coming here? It's this one, and it is coming here. I want to write the fluorine here and lithium here. What happens to the atomic number, lithium to fluorine? Increases. Nuclear charge? Binding energy? Yeah, so that is higher binding energy. Right? This is a higher binding energy. Right? Correct? That's what we learned earlier in the last slides. We learned that. Right? Okay. Why does XPS need UHV? That's what I mentioned already. Contamination of the surface can be controlled because it gets contaminated very fast. Contamination has to be controlled to while doing the experiment, you need to do the experiment at least you need at least an hour, for example. Your sample should be clean for about an hour, but that you need to have pressure of the order of 10 power minus 7 to minus 8, so that your sample remains clean. Okay. Now, removing contamination, but when you insert the sample, initially the sample will have some contamination, you have to remove that. So, for that people use the argon ion gun. They create argon ions and 3 kilo electron volts and bombard it on the surface. So, it removes all the contamination layers from the surface, right. Can cause damage to the surface, but it is negligible. Biological samples, if you are actually trying to record spectrum, one has to be little careful, biological samples, right, otherwise its damage is not very high. Okay. To create vacuum, you have to have all these things, for example, rotary pumps, oil diffusion pumps, mercury diffusion pumps, turbomolecular pumps, ion getter pumps, titanium sublimation pumps. Some of you know some of these pumps, Pirani gauges, ionization gauges, measuring pressure. Some of you may know this one, for example, oil rotary pumps. Have you seen that in the labs? In your organic chemistry lab, they use this Buchanan funnel and they filter, they connect it to some pump. That is nothing but that this oil rotary pump. That will create small vacuum, it decreases the pressure to of the order of 10 to the minus 3 torr. But what you require is a order of 10 to the minus 10 torr. Then you start using these things. Once you create this, then you go down, use these pumps to get the good vacuum, order of 10 to the minus 10 torr. And then pressure is measured by Pirani gauges, ionization gauges. Pressure is measured by Pirani gauges and ionization gauges. These gauges are calibrated using McLeod gauge. There is something called McLeod gauge, which is the primary gauge, which they calibrate this pressure using McLeod gauges. So, if you are not familiar, don't worry, but remember this, there is a procedure to generate vacuum. Vacuum technology is very important for these machines, for photoemission, photoelectron spectrometers. Okay, so this is something which I will leave it. Okay, now come to this X-rays on the surface of a solid. As I mentioned to you earlier, you have these layers of from the surface you have a top layer and then layers below the surface, right. So, you have this X-rays falling, these are dark, these lines are X-rays. These X-rays are penetrating into the sample, they are coming here and then they ionize these electrons and then these are top layer, electrons are coming out, these pink ones are electrons coming out from the top layer, they come out with correct information. But then the X-rays can go into the deeper layers, they also ionize them. By the time they come here, they lose some energy, they form basically, see these are the red ones, they will have less kinetic energy because they lose some energy in the process of coming to the surface, right, they lose some energy. So, these are you get all these electrons coming into the system from the surface, right. So, these electrons which are coming from after losing energy form a background. Over the background you have the actual spectrum represented by these pink electrons in the pink arrows. Okay. So, this is how it looks like. For example, here this is a spectrum here. So, this is the EF that is taken as 0 here and you have valence band here, this small thing is a valence band and then you have these levels, 2p levels, 2s levels. You also have KLL Auger lines here coming here and you will have some shake-up satellites, plasmon satellites and so on and so forth. So, it goes all the way up to 1s. So, here the binding energy increases from 0, from EF binding energy increases, kinetic energy goes in the opposite direction. It has to be like that, right? Okay. That is the typical XPS spectrum. So now all energies in the photoelectron spectroscopy are measured in electron volts. Unlike in IR where you measure energy in terms of centimeter inverse. But in photoelectron spectroscopy all energies are measured in electron volts. So 1 electron volt equal to 1.6 into 10 to the power minus 19 joules. Okay. So you measure the kinetic energy using the analyzer, and then from kinetic energy you can determine binding energy. Okay. Alright. So if you look at the carbon atom, for example, carbon atom has 6 electrons, 1s, 2s, 2p orbitals, 1s2, 2s2, 2p2. So you should get 3 different peaks in the spectrum. Okay. The largest one, the cross section out of all these 3, normally 1s electron, 1s peak is cross section is very high, it will give you intense peak. Carbon 1s, even oxygen 1s, even nitrogen 1s, his intense peak comes from the 1s electron. Okay. Some extra peaks will be seen because those extra peaks are basically Auger electrons, which I have already shown you. X-ray photoelectron spectrum also will contain some Auger emissions there. Okay. So what you have to essentially do is to analyze, you have to look at the core level binding energies, which if you look at the core level binding energies, then it will give you the signature of the elements. By looking at the core level binding energies, you will be able to find out the elements present in the sample, number 1. Elemental sensitivity via core level binding energies, and then chemical environment. Now the element may be present in the sample in a particular oxidation state. Oxidation state may be 0, +1, +2, +4, +6, etc. So because you are changing the charge, you are removing the electrons and you are giving positive charge, so the binding energy of the particular orbital or electron in a particular orbital is going to increase because you have the positive charge. From 0 to positive charge means that positive charge will influence the binding energy of the electron sitting in a particular level, right. So that is nothing but chemical shift. So this chemical shift will tell you what is the kind of oxidation state the element is present in the sample. Okay. So that is possible only in the core level shift, chemical shifts. Valence levels very difficult, they don't belong to any particular element, but whereas core levels they belong to particular element. So core electrons, if you analyze, you will be able to find out the oxidation state of the element, Now quantitative analysis can be done, but you need to have cross section evaluation, etc. Spectral line shapes, these are all some of the things which we can do, but I think I will give you some examples of that. Remember carbon 1s, ruthenium 3D, they come at exactly the same value, binding energy. This is so when you are actually recording ruthenium 3D, you say that it is ruthenium 3D, it may not be ruthenium 3D, it may be carbon 1s. There are a few things which you need to keep in mind. Similarly, argon 2p and rubidium 3p will come more or less at the same value. Okay. So when you are analyzing samples like ruthenium or carbon, if you think that ruthenium is there, then instead of 3D, you should record some other level. Okay. Or for example, 2p or 3p level you can analyze. Okay. Right. Now this is the electronic configuration of gold. Let us take gold has 79 electrons. These are all electrons filled up here. So when you start recording the spectrum, you should start seeing, from here to all the way down. Right. So many electrons are the 76 electrons, 79 electrons. Have you gone and counted? How do you know there are 79 electrons there? Carbon has 6 electrons. How do you know that? Hydrogen has only 1 electron. How do we know that? Huh? Is there any experiment? Photoemission experiment. So, if we have so many levels, then our photoemission spectrum should show some of them. For example, we may not go all the way to 1s because it requires very high energy. The energies that are available is only 1.2, 1.5 electron volts, which we are using, 1253.6 and 1486.6. So, with that energy, you will be able to analyze only these levels. That is enough for us to analyze the state of the element in the sample. Okay. You don't need to go to all the way to 1s, 2s, 2p, etc. That requires very high energy. It has no meaning, right. So, let us look at the spectrum now. So, this is the spectrum. This is gold 79. The magnesium K alpha is used, 1253.6 electron volt radiation is used to record this spectrum. This spectrum has, see this the red lines, these are all basically the peaks photoelectrons without energy loss. These are the electrons which are coming from the top layers without losing any kinetic energy. They are the ones which are giving the correct spectrum. Now, you see the background photoelectrons with the energy loss. See, these are all photoelectrons, there is the photoelectrons here. These are all energy loss, electrons which have lost their energy. They form the background. On the background, these are all superimposed. The actual spectrum is superimposed. The losses are because of the inelastic scattering, as I said, right. Loss process, inelastic scattering, and then they can prevent escape from the surface, and then phonon excitations, that phonon nothing but a collective excitation of atoms, though some energy is lost to the phonons, and plasmon excitations, this collective excitation of the electrons, some electrons get excited. So, these processes actually steal energy from the electrons which are coming from the bulk, little deep inside, they steal energy. That is why these electrons come out as a background here. They do not carry any information. They do not have memory of the where they are coming from. Whereas, the top layer electrons which are coming from the top layer atoms, they have memory. You can see these peaks are there. They have the memory. So, we need to analyze these things. What you see here is there is a strong, very intense peak, and then a less intense, etc. Can you see this? This is gold 4F. And this is gold 4D, this is gold 4P, this is gold 4S, gold 4S. So, that is enough up to your N is equal to 4 shell, N is equal to 4 shell. You do not need to go to N is equal to 3, N is equal to 2, N is equal to, you do not need to go there. This is enough. This spectrum, if you analyze, you will get all the information about the sample. Okay. Is that understood, all of you? Yes. Okay. Similarly, for example, take uranium. Uranium has 92 electrons. It has 92 electrons. So, this also has 4F, 4D, 4P. See, one of the interesting things that you should notice here, even 5D also. This is 6S, 6P, 5D, 5. See here. So, all these levels can be mapped. Okay. Right. One of the interesting thing is 4F electrons, there are 2 peaks here. F electron should give you 1 peak, but they are giving 2 peaks. What is the reason? Somebody has said you have learned XPS. Huh? Oh, this much you have not learned. I see. Okay. Okay. All right. Good. So, notice in this photoemission spectra, I am just giving you only 2 examples, uranium and gold, right. Let us look at once again. Gold has this spectra, each one is a doublet, this is a doublet, this is a doublet, and this doublet is very close, this doublet has little distance, the energy difference is there, the energy difference is more here in the case of P, in the case of D, in the case of F, and gold 4S, right, this is S orbital, S electron, right. So, what we are actually writing electronic structure of atoms, we are seeing here, this is experimental evidence that whatever we have learning, we have these orbitals, either atomic orbitals or molecular orbitals, etc. This is the evidence, experimental evidence for that. Okay, all right. Now let us look at this, why we have this two peaks here. We should get only one peak, but there is something here, some number is also there here, you see, there is some number. What are those numbers, what is it due to? So since I said there are only about 100 angstroms, that is the region from where you get this actually original spectrum. And whatever is coming here inside, you know, they lose energy, that forms a inelastic scattering tail. For example, this one, this background here, you see, you know, it says there is a background here, there is a background here, there is a background here. That background is coming from the electrons from the bulk. These are inelastic scattering background. Elastic, inelastic. Inelastic means they lose energy. Energy is lost. Right. So as a result, there is a lot of background also can be seen in the photoemission spectra. So there are methods to remove the background, but we will not go into those details. Okay. Let us look at again one more spectrum, aluminum foil. Since we are talking about aluminum foil, if you take, you know, what we use as to wrap something, you know, aluminum foil, right? You can see here in this aluminum foil, you have the aluminum is there, there is carbon is also there, there is carbon here, there is oxygen, there is OJ here. So there is a lot of oxygen is there, which means aluminum foil is oxidized. There is a thin film on the aluminum, which is oxidized. Aluminum oxide is there. Aluminum oxide is there, right? If it is a pure clean aluminum, this oxygen will not be there. It also has some carbon. Normally, many samples in nature, if you take, they will have some carbon. XPS will show there is carbon. All right. Okay, this is an experiment. This is an experiment which was carried out when I was doing PhD in 1986. None of you were there. Huh? 1986, I was working on this in this area. So one of my seniors told me, it's an examination, kind of examination for me. He said, show that Uj electron's kinetic energy does not depend on the source, the incident photon energy, or this is independent of photon energy. So this is the spectrum which I recorded in I showed some earlier electron spectrometers, right? One of the old spectrometer, that is the spectrometer which was used to record this. So here what happens is, you see here, this is copper sample, magnesium K alpha, this is aluminum K alpha. I use it to both these things. Now here the Auger peaks come at the same value. See that 800 around this. So it doesn't depend on the whether you use magnesium K alpha or aluminum K alpha. Whereas you see this one is the 2p level, copper 2p, and then this is coming here at around 500, whereas here it is coming at 300, right. So HNU is different, kinetic energy changes, whereas Auger electron kinetic energy will not change. This is a proof. Okay, all right. All of you got this point or not? Okay, good. Okay, now let us see what are these doublets that we are seeing. The doublets we are talking about is, suppose say I have an orbital. In orbital, how many electrons I can have? 2. Spin up and spin down. So these electrons will have 4 quantum numbers, n, l, ml and s, right. Now this is the initial state. I have not done my photoemission experiment. So what I do now, I remove this electron, photoelectron, and I have a single electron remaining here, right. This is the final state, this is initial state, okay. Now suppose say, now this electron has a spin, it has a angular momentum is there, L value, it has a S value also, there are two spins, right. Now once you remove that this electron, then it has its own spin, that spin interacts with the L value, right. So what happens now is, so that is, one is a spin, other one is orbit. L value is nothing but what? Orbits, right. S is a spin. So these two interact, give you spin orbit coupling, and that coupling lifts the degeneracy. Now it gives, it splits this energy level into two. Now here what happens is, now this is the spin orbit interaction lifts the degeneracy. Now this degeneracy basically, you see, this is the quantum number is, you have L and S quantum numbers, okay. Now the total quantum number, because of spin orbit interaction, is equal to J is equal to L plus S, okay, because the spin orbit interaction is there, right. You have a new quantum number J, which is equal to L plus S. Now you L value, suppose if it is a p orbital, this is a p orbital, what is the L value? P orbital, L is equal to 1, L value is equal to 1. Now S value, it can be either spin up or spin down, can be plus off or minus off. If it is plus off and minus off, you will get 3 by 2 and 1 by 2. Two different final states, two different, because of the spin orbit coupling, So that gives you, and also you can find out the degeneracy of that. Degeneracy is given by 2j plus 1. This is a j quantum number, 2j plus 1 is the degeneracy. So you put this j value here, this j value here, you will get degeneracy 4 and degeneracy 2. You see whether you get it, right. So as a result, the degeneracy is nothing but, this is proportional to the intensity, higher the degeneracy, higher the intensity. Now you see this, it gives you two peaks, these are the two peaks here, one is 3 by 2 and then 1 by 2, and these two peaks are because of this splitting, and the energy difference is because of the degeneracy that you have there, right. So this is 3 by 2 and that is half, delta, this is the difference between the two peaks is nothing but spin orbit splitting energy, So the intensity ratio is 0.5, half by 3 by 2, this divided by that is equal to 0.5, or if you take the other way around, it is going to be 2, either 4 by 2 or 2 by 4 is basically what you are looking at, okay. So that is the energy difference and that is the intensity difference. Now you know why intensities are different and why you are getting two peaks, the p orbital. Now you do the same thing for d orbital and tell me. Suppose I have a d orbital, dx square, one of the orbital, you have two electrons. Now I remove one electron. Now you have to tell me what are the spin orbit split. Do it, na? You can do it in your. So there, d orbital L is equal to 2. S is plus off, minus off. Find out the splitting. What about degeneracy? 2j plus 1. J is equal to 5 by 2 and 3 by 2. So you get 2, right. So that is how you can calculate. So accordingly, your experimental spectrum also should show that exactly what you are actually theoretically looking at. See here, for example, X-ray photon ejects an electron from the 2p level of silicon, so silicon surface. You have a silicon element, silicon surface. Now the spin angular momentum of the remaining electron in 2p level couples spin angular momentum, that is spinning. The spin angular momentum couples with the 2p with the orbital angular momentum. It is actually orbital, there is an orbital there, L, right? Spin moment, these two couple. Suppose if you don't ionize, then it will get 0, total value is 0. If you ionize, then you have net value, right? So that interact with the L value. So spin angular momentum couples with the orbital angular momentum. That is coupling between L and S. Coupling between L and S. That gives you lifts the degeneracy and gives you two peaks. And then the intensity is because of the degeneracy, which is given by 2j plus 1. That is how you start getting the splitting. But S value, S orbital, if you ionize, for S, L is equal to 0. So it doesn't give any splitting. There is only one single peak you will get. Single peak. Okay, that is how you should interpret. So this is what it is. Degeneracy of these two states, Gj is equal to 2j plus 1. Now ratio of the measured 2p photoemission signal. Now you calculate the area under the peaks. Area under the peaks, if you calculate the intensity of the 2p3 by 2 peak and intensity of the 2p half peak, you take these two, that should be equal to 2. Theoretically, that should also be equal to 2. That should also be equal to 2, right? Similarly, for d orbital, f orbital, etc. Okay. So that's what it is. You have to calculate you have to subtract you have to remove the background and then calculate that. You will be able to get that. Silicon 2p core level spectrum. Now, so this is spin orbit splitting peak radiation LS coupling. This is called LS coupling. So this is what I have given you here. Whenever you have this 2p3 by 2, this 2 is nothing but the principal quantum number. P is L quantum number. L is equal to 0, so and so on and so forth. And then so 0, 1, 2, 3, this PDF, SPDF orbitals, and this value is the J value. Okay. Now for P orbital, I already mentioned to you, area ratio should be 1:2. For D orbitals, L is equal to 2, area ratio should be 2:3. For L is equal to 3, F orbital, area ratio should be 3:4. That is why you get all these splitting in F orbitals, D orbitals and P orbitals, which I have shown you for gold and uranium. Gold and uranium. Okay. So now points to remember now. All of you pay attention. Points to remember. Number 1, for P, D and F peaks, doublet peaks are observed because of the spin orbit splitting phenomenon. Okay. For S electron, no doublet peak because L is equal to 0. The separation is due to spin orbit splitting. The values of spin orbit splitting of a core level of an element in different compounds are nearly same. What it means is that if there is a spin orbit coupling, P orbitals, D orbitals, etc., of a particular element, whether that element is present in any compound, that splitting is going to be same. Suppose gold, 4F, there is a spin orbit splitting energy is there, some X electron volts. That X electron volt is same wherever gold is present. It may be present in gold samples or it may be in a gold ring. That spin orbit splitting will be same. Energy difference will be same. Okay, all right. Oh, sorry. The peak areas, area ratios of a core level of an element in different compounds are nearly same. Peak area ratios are also same. The level with the highest J value has the lowest energy. because higher the degeneracy, lower the energy. That is nothing but your Hund's rule. Hund's rule. That is basically consequence of Hund's rule. Okay, all right. Yeah, so this is the same story. So I am just showing you quickly copper 2p photo emission, 2p 3 by 2, 2p half. The spin orbit splitting energy is 19.8 electron volts and peak area is equal to 1:2. P orbital, it has to be 1:2. Okay. Now, I have also given you this L is equal to 1, S is equal to plus minus half. So, you have J is equal to L minus S, L plus S, half and 3 by 2. So, that is how you get your doublets. Similarly, for example, gold 3D, 3D 5 by 2, 3D 3 by 2. This has a lower energy and that is a higher energy. The spin orbit splitting energy is 6.0, peak area is 2:3. Okay, that you know how to calculate now, right? All of you. Now this is gold 4F. This is 3.65, 3:4 peak area. So this is the gold 4F photo emission spectrum. There is something called Koopman's theorem. Is anybody else waiting for after this? I'll take a few more minutes and then finish this. Okay. Koopman's theorem. The Koopman theorem says, Koopman is a person who says, if I have a system with n electrons, I have a binding energy of a particular electron. If I remove that electron, one of the levels, then the energy difference between the initial state and final state should be equal to the binding energy. That is correct, no? I have a system before ionization, I have a system after ionization, right? The energy difference between these two should be equal to binding energy of that particular orbital where electron is ionized, right? The binding energy of electron is simply the difference between initial state atom with n electrons and the final state atom with n minus 1 electrons, ion, and free photoelectron. This is the final state, that is initial state. Difference should be equal to binding energy. That is what normally we think of, right? But it is not so straightforward. There are a lot of other things happen there, right? There are a lot of things other in electron correlation. There are so many other things which come into picture. Sometimes it changes. This is ideal. This is ideal. Ideal gas, ideal solid, ideal liquid, right? What is ideal gas? No interactions, no van der Waals interactions. Ideal solid, ideal liquid, ideal human being. You have any ideal human being on earth? So go find out what is ideal solid, ideal liquid, ideal gas. I am in a class, I will talk to you later. I am in the class, I will talk to you later. Okay, all right. So this is ideal one. But anyway, because of these binding energies, sometimes what is measured in the spectrum and what is calculated is going to be different. There will be some 10 to 20 electron volt difference is there. That is because of the electron rearrangement shield the core hole, and also electron correlation. These are some of the effects which you will probably learn when you come to higher studies. If you come and join here for PhD, there are faculty who are working in these areas here. They will teach you more. Okay. There are other things, shake up and shake off satellite process in photoemission, right? You remove an electron, these photoelectrons are removed, but what happens is some of this energy of this is stolen by this electron which is sitting in a higher level. As a result, the kinetic energy of the photoelectron which is coming out is going to be smaller. Even from the top layer, the kinetic energy is going to be smaller than what is expected. So that gives you satellites in the photoemission spectra. This is what it is. You see, this is the original spectrum, but then they have satellites. These are called satellites. The satellites are mostly seen in copper oxide and copper metal. Copper metal doesn't have that satellite, but copper oxide, copper 2 plus here, that shows the satellite here. These are satellites. Copper sulfate, this is copper 2 plus is there. There are satellites here, right? These satellites are because of this phenomenon, right? They're all little okay. Don't worry too much about, but there are some satellites here, right? So people thought these satellites are nuisance, but now the younger generation started using them as a extracting some information out of that also. All right. Okay, all right. Don't worry about that. There is a multiplet splitting. There are peaks which are these are shake-up peaks and there are multiplet peaks. Don't worry about all this. I think we will skip that. But what is important here is this one. Here, some of you who are interested in this, you should go read Modern Spectroscopy, 4th edition by Michael Hollas. That is a book where there is one nice chapter on photoemission spectroscopy. All of you go read that. That's a very good, you can understand after going through this little bit of this introductory lecture, you will be able to understand that. Go read that. Nice chapter. You will be able to understand that. I recommend all of you read that. That book is available. Okay. So here, what is one of the important things about photoemission spectroscopy is chemical state identification, inspection of bonding environments. Now let us look at this molecule. This molecule is nothing but ethyl trifluoroacetate. Ethyl trifluoroacetate. It has how many carbons? 4 carbons. So if you record carbon 1s spectrum, how many peaks would you expect? Now don't look at that. You tell me directly without looking at that. All are carbons. No, why should you get 4? 4 carbons, 4 carbon 1s. That is the point here. These carbons, if you look at from organic chemistry point of view, this fluorine has higher inductive effect, negative inductive effect or positive? Negative inductive effect, right? So the electron density is less here. The electron density is much less compared to this place, and this is compared to this place. This is much less compared to this, and compared to this is much less. So the electron density around that carbon is changing. Delta plus is different. Delta plus is not same in all carbons, right? The moment you change the electron density, that will affect the binding energy of the 1s electron. As a result, you see 4 different peaks. This peak is because of this carbon, this peak is because of this carbon, this is because of this is because of this. Which one will have higher binding energy? This carbon, 1s carbon, 1s of this carbon or of this carbon? Binding energy, 1s binding energy of which carbon will have a higher 1s binding energy? This carbon or this carbon? Carbon attached to fluorine. You can see here binding energy here. This is the highest binding energy, around 294 or something, and this one is only 284. So this is chemical shift. The same thing you have heard in NMR, similar thing in NMR also. So this is chemical shift of in photoemission spectroscopy. Okay, you can see here also silicon and SiO2. Pure silicon will give you a peak around 99.15 electron volt, but the moment you oxidize it to silicon 4 plus, it changes about the 4 electron volt difference is there. SI volt, silicon 4 plus has a higher binding energy. Higher binding energy. So, by looking at this, you can easily identify the oxidation state. That is possible. That is possible. And this one is XPS of a sample of a moon dust. Somebody has gone to moon and brought the dust and recorded XPS. So, what is it telling you? Moon dust, XPS spectrum. Moon has the same elements that we have. It has all magnesium, aluminum, potassium, calcium, titanium, nitrogen, oxygen, carbon. They are also there on Earth, right? So, it tells you the moon's dust sample has, you have been able to identify the elements present in that. The sample have all these elements, right? So, this is used for elemental analysis. If I have a sample, what elements is present? You record the XPS and then find out the elements present. Okay. This is a spectrum, XPS spectrum of ammonia synthesis catalyst. Ammonia synthesis catalyst is, what is ammonia synthesis catalyst? Haber process, you know. Iron, right. So, somebody has analyzed this. It says the iron has the ammonia synthesis catalyst has potassium, iron, aluminum, silicon, oxygen, etc. So, it is not only iron, it has some promoters, aluminum oxide, potassium, right, and some silica. It's a very dirty catalyst. Of course, it has iron is very important. It has lot of other promoters, so that you know the catalyst works. So, this is the XPS spectrum of that. I will skip this one. You see this one, some of your organic, how many of your inorganic chemistry? General chemistry. Now, you see here this is a platinum metal, platinum 4F. Now, same platinum is now present in this complex here. You see this platinum which is surrounded by NH2, NH3 I think this is right. NMe, methyl group and there is one chlorine group. Now, this platinum is surrounded by 3 chlorine groups, 2 NMe2 I think, right, yeah. Now, you see this is platinum is 0, this platinum is 2, this platinum is 4, you see the binding energy is shifting from here to here to here, right. So, beautifully you can easily see. So, what people do, they make these compounds, these complexes and then record the spectrum. You can clearly see there is a shift. So, from this you can easily identify platinum as 4 plus, platinum as 2 plus with respect to platinum, right. It is a nice example. I think I will skip all this, This is another interesting slide which I want to show you. In this case, what people have done is, this is what you are seeing here is a photographic film. This is done some 100 years ago. So, those days there is no computer, nothing was there. So, they used to, when electrons are coming, you know, they put this photographic plate and expose it and then develop it. So, they saw there are 2 lines here. Those lines are nothing but 4F, 7/2 and 5/2. People have done those days, nothing was there, right. Same 2 peaks now you see here, we are recording it, 4F, okay. This was done long back, maybe this must have been done at least 100 years back, this one, all right. Now, this is a clean gold foil, you can see this 4F, 7/2 and 5/2, 4D peaks are there here, 4P, right. Now, they will take out this the clean foil, put some dirty finger on that, which has some grease or something. Now, this says, spectrometer says it is not gold, it is only silicon and some carbon, no gold. It says there is no gold there. You believe the spectrometer or you believe yourself? You know you have put gold only, but it says it is not gold. What does it tell you? It is surface, it shows a surface sensitivity. Only up to 100 angstroms or 110 angstroms electrons only it can detect. And that there is a thin, there is some contamination is there on the surface. It is not seeing going beyond that. So this is an example of how surface sensitive XPS is. Okay, this is a very interesting example. Surface sensitivity of XPS. Okay, all right. This spectrum, this is one of the things. This is the actually sodium azide. N3. What is the electronic structure of N3? How does it N3? N is sodium is plus, N3 must be minus. How will you write N3 minus? 3 nitrogen atoms. So XPS gives you, XPS is recorded, nitrogen 1s is recorded here, nitrogen 1s photoelectron spectrum is recorded. It shows two nice peaks, one is very intense, other one is half of that. So it immediately tells you that this is at higher binding, this is at lower binding energy, this is at higher binding energy. That higher binding energy means there are two nitrogens with different charges. Higher binding energy nitrogen should have positive charge, so that is this one, and then the lower binding energy should have negative charge minus, and then it is intensity is twice, so there must be two nitrogens with negative charges and one nitrogen with one positive charge. The ratios are also, intensity ratio is also matching with this. So this is the structure of this azide ion. Okay, all right. So that is how one can actually use this. This is what it is. The sodium plus that and nitrogen positive is the center one, other one two are negative. So that is exactly is reflecting in the N1s spectrum of azide, XPS N1s spectrum of azide. Okay, I think I'll stop this here maybe, but photoemission spectrum of gas phase molecules, you still have energy to absorb? Huh? You want to absorb this also? You have time? Half an hour over, huh? Okay, I'll stop here. Okay, since they are interested, just 5 minutes you give, huh? Yeah, okay, 5 minutes. So, UPS spectrum. UPS spectrum of molecules. Take carbon monoxide. If you have carbon monoxide, you can see this kind of thing in the book Physical Chemistry by Macquarie and Simon, chapter 9 and chapter 10. Yes, he talks about this. Physical Chemistry textbook. Now here, see, you have these molecular orbitals, right? You see, these are all molecular orbitals, 5 sigma, 1 pi, 4 sigma, 3 sigma, etc. You remember that? Electronic structure of carbon monoxide are diatomic molecules. Molecular orbital diagrams. Molecular orbital diagrams. Now, how do you know that these molecular orbitals are existing? This is example. Molecular orbitals. Now, if you can ionize these electrons, these are all molecular orbitals, their energies are very small, when energies are only less than 40 electron volts. So you can do ultraviolet photoemission spectroscopy here. Okay, all right. If you do that, look at this hydrogen. It is 2 electrons form the bonding orbital here, one sigma, one s. Now I can take this hydrogen and ionize it. Remove one electron, photoionize one electron. If I remove photoionize one electron, a molecule plus photon gives you molecule plus electron. So this is the ionization energy is equal to E minus kinetic energy. Here we call it ionization energy, not binding energy. Okay. Now what kind of spectrum can you expect? So, this is the spectrum that you get. This is the spectrum that you get, because you know the this is the potential energy diagram, and this curve what you are seeing is the psi square, that is the vibrational levels. Now, it has all vibrational levels, right? Molecules have vibrational levels, right? So, this vibration level, ground vibration level, from here if the molecules are sitting, mostly molecules sit in the ground vibration level at normal temperature, and then there is a it has a wave function psi in quantum mechanics. So, this curve what you are showing is a psi square. So, the probability of this molecules is maximum here, and then from here it goes to this level. This is nothing but, this follows the Frank-Condon principle. This follows the same Frank-Condon principle that we have learned in UV visual spectroscopy. So, from here it goes to here. Suppose somewhere this side and that side, it will end up somewhere here and here. But this is more intense peak comes from the peak here to this. That is the one which gives you most intense peak, and all others will have smaller peaks. So, it gives you a vibrational progression. If you record this photoemission spectrum, ultraviolet photoemission spectrum of hydrogen molecule, if you record, you get a spectrum something like this. That is because of the vibrational levels. The excitation takes place in different vibrational levels. This is the spectrum of hydrogen, ultraviolet photoelectron spectrum of the hydrogen. Okay, all right. This is the ultraviolet photoelectron spectrum of nitrogen, right. So, these are all vibration progressions. So, this is nothing but Atkins' book. I have given you these molecular diagrams, right. Okay. Because this is the ultraviolet photoelectron spectrum of oxygen molecule, you get a vibrational spectra. This is given in Macquarie book little bit, also probably in Banwell. Banwell also gives some idea. Okay. So, that quickly I went through, and summary is HNU is equal to kinetic energy plus binding energy. Laboratory photon sources are these. Surface sensitive technique, sensitivity is 2 to 50 angstroms, not 50, okay, 100 angstroms. Spin orbit coupling, gives you doublets in PDF orbitals. Intensity is dependent on the degeneracy 2J plus 1. Chemical shift XPS depends on the chemical environment. High bending energy satellites appear due to shake-up process, example copper oxide. Gas phase photoemission spectra show vibrational fine structures, examples hydrogen, nitrogen, oxygen. So, that is basically what it is. Okay. So, if some of you are interested, you can read this paper. This is my essentially this in 1991. This is 80% of it is my thesis, PhD thesis. Okay. Do you know this person? How many of you heard this CNR Rao? Go Google it. Have you heard of him? Have you heard? Go Google it, CNR Rao. Okay, noted down all that. Okay, so this is the so this is the spectrum. This is the book by Professor P.K. Ghosh, Introduction to Photoelectron Spectroscopy. He is the person who tried to build photoelectron spectrometer in India. He built actually gas phase spectra, but solids he could not do that. He is a person, he is still alive. He is the one who actually wrote this nice book, Photoelectron Spectroscopy from India. He is there, he is in Calcutta somewhere. He is a good, very nice, very good teacher. Okay. And this is another nice book, but the book is out of print, but this is a book which everybody should read. This is out of print. I had a book that I lost it, somebody took away, some student or somebody has taken away. Okay. I think with that I stop here, and thank you.
SwayamPrabha. Digital India. Educated India.